together a whole bunch of ideas that we've been working on over the last couple of weeks and solve problems involving what are called general projectiles. So, a quick review: if we launch a projectile at an angle that is not horizontal, so we launch a projectile at some angle above the horizontal like this, then we can find the components of the velocity in the x and the y direction, and this tells us how fast it's moving initially in the x direction. We call that vx initial. And this one tells us how fast it's moving in the y direction. And a little bit of trig, and you can work out that the velocity in the x direction initial is equal to the initial velocity, how fast it's launched, times the cosine of the angle. And in the y direction, we get v0 times the sine of the angle. So when we're solving a problem and an object is launched at some general angle with an initial velocity, we can break it down and figure out how fast it's moving horizontally and how fast it's moving vertically with these two formulas. So we're going to put that together now and solve a problem that involves a general projectile. So the thought experiment I want to do is just take a quick look at what happens if we launch a projectile at 50 meters per second at an angle of 36.87 degrees. So we're going to launch the projectile kind of like this. Okay? So what we're going to do is figure out how fast it's moving in the x and the y direction initially. So the initial velocity in the x direction is v0 cosine theta. You put in 50 times the cosine of 36.87 and you get 40 meters per second. So our projectile is going 40 meters horizontally every second. In the y direction, we plug in v0 sine theta, and it's going 30 meters per second upwards. So every second it goes over 40 meters, and if there was no gravity, it would go up 30 meters. So what we're going to do is we're going to plot where the projectile would go if there was no gravity. So in 0 seconds, it's down here at 0. So what we're plotting is here where it is in the x and the y direction. After 1 second, it's gone over 40 meters and up 30 meters. So every second it goes over 40 and up 30 meters. In another second, it would go over another 40 and up another 30. In another second, it would go up over another 40 and up another 30. And it would keep doing this until it just left the Earth, if there was no gravity. But of course there is gravity, and gravity will affect its motion in the y direction, not in the x direction. So we worked out before in one of our warm-ups that if you drop a ball and you let it fall for 0 seconds, it falls 0 meters. If you let it fall for 1 second, it falls 5 meters. In 2 seconds, it falls 20 meters. In 3 seconds, it falls 45 meters, etc. So we're going to use that. We're going to say, okay, this blue sequence here is where the ball would be every second if there was no gravity. But if there is gravity, what will happen? Well, at the launch, it'll be right here, down in the bottom left corner. 1 second later, it will go over 40 meters. It would have gone up 30 meters, but because of gravity, it's going to come down 5 meters from where it was. So it's actually going to end up right here. Okay? So it would have been here. It's now 5 meters below. In 2 seconds, it'll be 20 meters below where it would have been without gravity. So in 2 seconds, it's going to go over another 40 meters. It would have been here without gravity. We're going to go down 20 meters. So 5, 10, 15, 20 meters. It's going to be right about here. After 3 seconds, it would have been here, and it's going to be 45 meters below that point. So that's going to be right here. And if you were in class, we would be actually making this graph, plotting the points on an actual graph. After 4 seconds, it'll be 80 meters below where it would have been without gravity. So if you go down 80 meters from this point, you get right here. After 5 seconds, it will fall 125 meters from where it would have been without gravity. So that's down here. And after 6 seconds, it'll fall 180 meters, and this is 180 meters up, so it hits the ground. So our little thought experiment will tell us that if we launch a projectile at 50 meters per second at 36.87 degrees, it will be in the air 1, 2, 3, 4, 5, 6 seconds about. And during those 6 seconds, it will go somewhere around 240 meters sideways. So it'll land about 240 meters from where it started. Okay, so that's a little conceptual thought experiment. We're now going to solve that problem in detail using our equations. All right, So what we have is a golf ball, and it's hit on a level course. Now it's the golf ball that's going 50 meters per second, and initially it's going 36.87 degrees above the horizon. Okay, so that's the launch angle. We want to find the range of the golf ball. So we have a level golf course. It's hit from the ground. It goes up, 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 down, 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 hits the ground. Okay? So we are going to solve this problem using what we know about projectiles. So remember, we have our double variable list. We need to figure out what we know. We know that the acceleration in the x direction is 0. And we know the acceleration in the y direction is also negative 9.8. And delta y is how far it ends up compared to where it started. So we know it starts on the ground and it ends up on the ground. So delta y ends up being 0. And of course, the acceleration in the y direction is negative 9.81. Okay, so when we solved horizontally launched problems, we knew that the velocity in the y direction initial was 0. But we don't know that anymore. We got to figure out how fast it's going initially in the x and the y direction. So the first step in our solution is to find the velocity in the x direction using this equation. I can plug in my numbers, and I get 40 meters per second. This is the example we did previously. The horizontal velocity is 40 meters per second. In the y direction, I can find the initial velocity, and that's v0 sine theta. So I plug in the initial velocity times the sine of the angle, and that's 30. So now I know the velocity initial in the y direction as well. Okay, so now we're going to go back to what we used to do when we did projectiles that were horizontally launched. We are going to solve this equation for t. The problem is the initial velocity in the y direction is not 0 anymore, so you can't cross this term off. The initial velocity in the y direction is now 30. So in order to solve this for t, we're going to have to use the quadratic equation. So when we're solving with the quadratic equation, I'm not going to force you to make algebraic solutions. We're going to go ahead and put in our numbers. Delta y is 0. And so that equals, I'm just going to put an extra 0 here. The initial velocity in the y direction is 30, so I'm going to get 30t. 1/2 of the acceleration is negative 4.905. Remember, the acceleration in the y direction is negative 9.81. You take 1/2 of this and you get negative 4.905. So I added this extra 0 so that it looks like a quadratic. So I have 0 on the left. This is c, this is b, and this is a in the quadratic equation. Okay? So we're not going to worry about units or algebraic solutions for these. We're just going to try to solve them with the quadratic equation. The quadratic equation says that the solution will be minus b, so negative 30, plus or minus the square root of b squared minus 4 times a times c. But because c is 0, this term is going to go away. And then we divide that by 2 times a. So I'm going to plug this in my calculator, and if you're struggling with this part, talk to me or let me help you. And if all else fails, get a quadratic equation solver online. Plug in a, which is negative 4.905, plug in b, which is 30, plug in c, which is 0, and it'll give you the two solutions for now. The two solutions are 0 or 6.12 seconds. We choose the positive solution, so the ball is in the air about 6.12 seconds. And once we know the time, we can now solve the x problem. Okay? So this is just like we did with horizontal launch projectiles. We know the acceleration in the x direction is 0, so that term gets clobbered. We're trying to find delta x, so we put in the initial velocity in the x direction, which we found up here. We multiply that by the time, and we get the range of the projectile. So this golf ball goes 245 meters horizontally before it hits the ground. And that agrees very well with our little thought experiment. We got 240 meters for that. But that was a bit of approximations. So this is a more exact answer. Okay, so that's what we're going to do. It seems like a lot of work. Make sure you enumerate your solution. You'll have this as an example. We're going to find the components of the velocity in step 1 and step 2. Step 3, we're going to solve this equation for the time, which will involve the quadratic if the initial velocity in the y direction is not 0. And then, once we know the time, we can find the horizontal range, the distance it moves horizontally. Okay, another quick example just to show you what it looks like in a slightly different situation. If the ball is thrown from the top of a building, then it's going to look something like this. the ball starts here, it's thrown upwards at an angle, it goes up, 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 down, 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 and in this case there's just a small change. We know that the acceleration in the x direction is 0. Delta y is the distance it goes in the y direction. It starts here, which is 30 meters high, and it ends here at 0. See my coordinate system? There's my x and y axis. So delta y is negative 30. It ends up 30 meters below where it started. Okay? We also know the acceleration of the y is negative 9.81. All right, so we're going to do the standard thing. We're going to evaluate this expression and find the velocity in the x direction. Plug in the numbers. It's going 8.6 meters per second every second in the x direction. In the y direction, the initial velocity is v0 sine theta. We put in the initial velocity and the sine of theta, and we get 12.3 meters per second. We're now going to solve this equation for time. Delta y is negative 30, so I'm going to get negative 30 equals the initial velocity in the y direction, which I got here, 12.3 t, minus 1/2 the acceleration, which is 1/2 of negative 9.8, so that's negative 4.905 t squared. The quadratic has got to equal 0 on one side, so I'm going to bring this term to the other. So although it's negative 30 in the equation, when I bring it to the other side, it becomes positive 30. So the coefficient of the t squared term is a. Here's a. The coefficient of the linear term, t, is just b, and this is c. So I can use the quadratic equation to get minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. I evaluate that in my calculator, and I get two solutions. T could be 4.02 or negative 1.59. Since t is a time, we can't have a negative time. We're not going to use that solution. It is extraneous. We're going to use the positive solution, which is 4.02 seconds. So now that I know the time, I can evaluate this expression to find the distance it moves horizontally. So the distance it moves horizontally will be calculated. The acceleration is 0, so that goes away. So I simply plug in my initial velocity in the x direction, which is 8.6 meters per second. Multiply that by the time, which I found up here in step 3, 4.02 seconds, and that will tell me the range, or how far it goes horizontally. So this object lands 34.6 meters horizontally from where it started. All right? So that's the process we're going to follow when we solve these general projectiles. So you've got some practice problems. If you get stuck, make the variable list, figure out what delta y is, and then using the initial velocity in the x and the y direction, you can solve this equation for the time. If you're getting bogged down solving it, try using a quadratic formula solver online. Once you find the time, then figure out how far it goes horizontally. All right? Okay, good luck.